Okay, let's pause for a moment and remind ourselves where we are. We've talked quite a bit about diagonalizing matrices, and then we talked about Jordan form. And the idea was we have a matrix A, and we want to find an invertible matrix S, change a basis matrix such that S inverse A S is as nice as possible. Diagonal is great, and if you can't make it diagonal, then you use the Jordan form. So that's pretty much what we talked about last time. Now I want to go back to the diagonalizable case and talk a little bit further about that. So recall this matrix S, when you're diagonalizing a matrix, is made up of the eigenvectors, and the diagonal matrix that you get is made up of the eigenvalues. And we've talked about this before. A is diagonalizable if and only if it has a basis of eigenvectors, because then you can use those to make this matrix S to make it diagonal. Okay, here's the main point. Not all bases are created equal. A basis is particularly nice if it's orthonormal. That's because an arbitrary basis is an arbitrary basis. The vectors could be more or less anywhere. In an orthonormal basis, they have length 1 and they're perpendicular. That's particularly nice. So we'd like to focus on those kinds of matrices. That is to say, matrices A, where such that you have a basis of eigenvectors and that basis is orthonormal. So how do we tell if we have such a matrix? Can we think of an example? Well, let's remind ourselves how this works. So we have this matrix S that we make up out of the eigenvectors, and so S diagonalizes A. And remember, if you make a matrix out of a bunch of vectors, you can tell if it has orthonormal rows or columns. That's if and only if it's orthogonal. I'm sticking to the case of real matrices here. So we're interested in the following situation. I want an orthogonal matrix Q, that is to say, it satisfies this condition, such that Q inverse AQ is D. It diagonalizes A. Now this equation should look familiar to you, and I suggest you pause the video for a minute and think about that and go back and see where we've seen something like this before. Well, here it is. This condition, Q transpose, up here says the Q transpose is equal to Q inverse. So I can write this equation as Q transpose AQ is equal to D. And we've seen that this holds for symmetric matrices. Okay, so let's go back and quickly look at the complex version. Remember, symmetric becomes Hermitian, and orthogonal becomes unitary. So we're looking for a matrix which can be diagonalized by a unitary matrix U in the complex case. And here's a very big theorem in linear algebra. This is called it's so big it even has a name. This is called the spectral theorem. And it says the following. Suppose A is a symmetric matrix, if you're working over R, or a Hermitian matrix, if you're working over C. Then A has a basis, an orthonormal basis of eigenvectors. That is to say, that's exactly the same thing as saying you can find an orthogonal matrix in the real case, or a unitary matrix in the complex case, such that Q inverse AQ is equal to D, or U inverse AU is equal to D. This matrix can be diagonalized by an orthogonal or a unitary matrix. Okay, let's pause for a minute and let me summarize what we've just gone over. The idea is we're starting with an arbitrary matrix A, and we want to find an invertible matrix S such that S inverse AS has a nice form. Well, you can always use Jordan form. Any matrix can be put into Jordan form. That's in some sense the worst case. A better case is if you can diagonalize it. It's always nice if you can diagonalize. And that's equivalent to it having a basis of eigenvectors. That's a misprint there. And, well, now we've talked about the fact that even better is if you can diagonalize it where the eigenvectors are orthonormal. From this point of view, that's the best possible situation. Okay, so we've seen that 3 holds. You're in the best situation if A is symmetric, or Hermitian in the complex case. What about 2? Well, 2 certainly holds if the eigenvalues are distinct. That's a simple case. But unfortunately, if the eigenvalues are not distinct, it might still satisfy this. And it can be sort of hard to tell. So there's not a nice elementary test for whether a matrix is diagonalizable or not. And then finally, if all else fails, you use the Jordan form. And I want to emphasize this case 3 is the spectral theorem. All right, I want to say one last thing about this topic. I want to look for more general matrices than the ones we've just considered, which have the property that they can be diagonalized by a unitary matrix. And I'm just going to talk over C now. So here's a new definition. A is an n by n complex matrix. We say it's normal if the following condition holds. A times A bar transpose is equal to A bar transpose A. Or using the H notation, it says this. In other words, A and AH commute. If you multiply them in either order, you get the same thing. So that's a kind of condition we haven't seen before. How do you find such things? Well, there's an obvious example. If A is Hermitian, then A is equal to AH. So obviously it commutes with AH. A times AH is AH times A, because the two things are equal. So that is to say, Hermitian implies normal. Now, there's another class of matrices which are obviously normal, which is unitary. Why is that? I'm claiming that if U is unitary, U bar transpose U is equal to, well, is equal to U bar transpose, and the reason is both of those things are equal to I. So normal matrices capture both Hermitian and unitary. And here's the second part of the spectral theorem. You have an n by n complex matrix A. Then it's diagonalizable by a unitary matrix. That's the condition we've been talking about. If and only if it's normal. So that is to say, there are matrices which are not Hermitian, which satisfy this property, and this theorem exactly tells you which ones they are. And as I said on the previous slide, this holds for Hermitian matrices, it holds for unitary matrices, but there are others. Here's a silly example of a matrix which is neither Hermitian nor unitary, but for which this holds. Just take a diagonal matrix with any numbers down the diagonal. Well, then it's certainly not Hermitian, and it's not unitary if the zi's are not special. And in the case of Hermitian, they have to be real, and for it to be unitary, they have to have absolute value 1. But it's obviously normal because it's already diagonal. You can diagonalize it by using the matrix U is equal to the identity, and it commutes with its transpose bar. So let's look for a less silly example, and here's one that I'm going to pull out of my hat. This matrix A is normal. Now, it's a real matrix, but you should think of it as being a complex matrix. Its bar transpose is just its transpose that looks like this, and let's compute. If you multiply it in this direction, you get this matrix, and if you multiply it in the other direction, you get, let's see, this matrix. It turns out they're equal. A bar transpose is equal to A bar transpose A. So this is an example of a matrix which is normal, but not Hermitian or orthogonal. Okay, that's a good place to stop. See you in class.